Hello, everyone. So this video will talk about another algorithm to find the optimal route or Hamiltonian path. And if you'll recall, we had one algorithm last time, which was called the brute force algorithm. And the main problem with the brute force algorithm was it took a long time. So you have to go through every single possible Hamiltonian circuit, or maybe you can divide by two, but still that number is a large number if you have a complete graph with a lot of vertices, and you have to add up the total cost or total weight of the different routes that you get, the different Hamiltonian circuits that you get. So we're going to get another algorithm to find an approximate optimal solution. So this, as we'll see, is not always the optimal solution, but it gives us a fairly quick way to get a better than average solution, let's say. All right. So what is this is called the nearest neighbor algorithm. And so what does it do? Well, the first thing you need to do with the nearest neighbor algorithm is you need to choose a place to start. And so I've got a graph drawn here, and let's start with A, our point A. And what we do is we look at all of the edges incident to A, which I'm circling here, and we check their values, and we find the smallest value, okay? And so, in other words, we find the smallest weight, we find the smallest cost, we find the edge with the smallest number on it. And then we follow that edge. So let's follow that edge. We'll make it, bold, and we will follow this edge. Okay, now we've gotten to the next point, C. And we look at, and we do the same thing, except now we only look at those outgoing edges that are incident to vertices that we have not already visited, unless we're at our last vertex. So here we find the smallest number that we can, which in this case is 1, and we follow that edge. Okay, so we'll go here. And now, again, we look and we have 3 possibilities. We can't choose this possibility because we've already visited A. So we eliminate that. We've got 3 possibilities. The smallest number is 5. So we'll choose this edge here as our nearest neighbor. So why are we calling this nearest neighbor? Well, sometimes when you think of this as a route problem, that number could be like the distance, how far away that neighbor is. So you could think of that number as telling you, okay, for the first trip, it's 2 miles away from A to C. And then from C to B, it's 1 mile away. And then B to F is 5 miles. Okay, so that's why we call it nearest neighbor. All right, now we're at F, and again, F has 5 edges coming out of it, but these first 3 edges are the top 3 edges. They're going to vertices that we've already visited, so we don't want to go to those. So we'll just look at these 2, and well, happily, the nearest neighbor is E, but we will follow this edge without smallest weight. Okay, oops. Continuing. We only have really one choice here, so we can get, I mean, we can't return to A. So again, if you look at the options, these 4, we've already visited the vertices, the neighbors. So the only neighbor that's been unvisited, or that has not been visited yet, is D. So we will go ahead and visit D. And then now we're at the end of a sort of a path, a Hamiltonian path, and we just have to connect up to D. Okay, so this is a fairly straightforward algorithm. However, there are some subtle things about it that maybe one could notice. So let's see what the total. Let's consider this as a cost function, as a distance function. So we can think of this, each of these costs as being the number of miles or how far apart the vertices are. So how far did we go on this trip? Well, from A to C we had 2, and then we added 1 from C to B, and we added 5 from B to F, and then we added 1, and then we added 1.2, and we added 2.2. So our total cost, if you will, for this route was, let's see, 8, 10, I will say 10, looks like 12.4. Forgive me if my arithmetic is a little shaky, but I believe it's 12.4. Okay, and so, but now I would contend that you could actually look at the following route. So we could have gone this way, just around the perimeter. And if you look at this route, what do we have? We have 2.1 plus 1 plus 1.3. Oops, I guess I really shouldn't have done that. I guess I should have gone. I didn't hit F, so I need to go to 1.3 plus 1 plus 3 plus 2.2. And let's see. So if one puts this into a calculator, it looks like we have 5.3. So again, my arithmetic needs a little work. 5.4 plus 5.2 is 10.6, if I am adding that correctly. So I just gave, okay, so what am I trying to talk about? What I'm saying is, okay, here's another Hamiltonian circuit that I looked at, and actually I initially looked at it and I thought, okay, go around the edges, but I forgot about my center vertex. So then we just adjusted it and went inside. And we see that when we add up the total cost there, we get 10.6, which is smaller than 12.4. So what we see here is this is an algorithm. It isn't, nearest neighbor algorithm is a good algorithm to use. It does indeed get us something better than if we maybe just randomly um, chose a route. However, it doesn't give us the optimal. Typically, it will not give us the optimal. It might, but it typically will not give you the optimal route. So that's something to be aware of. This is what's called an approximate algorithm, and your optimal solution uh, is not always going to be produced in this algorithm. All right. Well, with that said, um, I want to take a second and do something that, well, I don't think we've quite done yet with graphs, but is a very typical thing to do, and especially if you ever um, want to do some computational thing on a computer with it. One thing that you can do with a graph is you can sort of convert it into a table. Mathematicians would say we would convert it into a matrix, but the way you do this is you associate um, to any given edge a particular entry. So if I look at this edge, I see that my vertices are C and E. And so I will look at a box, say C and E, and I will put in the weight in that box. So there is a little bit of ambiguity here because there's also a C and E down here, and usually you just write the same number in both sides, unless you're dealing with something called a directed graph, but we're not going to, well, at least at the moment, we're not talking about that. So, so I want to fill this table in using the using this process I just described with the weights, and then we'll see how there's another way rather than drawing these pictures, which can get kind of complicated and hard to manage. You can kind of play with this table instead, and it's a little bit easier. So let's see how first to convert from the graph to this table. All right, so I'll go along a row, and the way I'll do it is I'll look at all of uh, the edges connected to A, and I'll find these. That's going to give me these entries, and I'm just going to do this upper triangular part here, and then we'll just kind of flip it and get the rest of the values. All right, so AB has value 2.1. AC has value 2. AD has value 2.2. AE has value 3, and AF has value 3. And so, again, what I'm doing to find these values is I'm looking at the weights along an edge. So here I see this weight connecting A and F is 3. So I look at A, I look at F, and I find the corresponding entry, and I put the number in. Okay. Hopefully that makes some sense. So now I'm going to look at B, but I'm going to look at only the values over here. So I want to look at BC, BD, BE, BF. Okay, so, and then I'll just enter those values in. BC is value 1, BD is value 7, BE is value 8, and BF is value 5. Great. Moving on, I can go to C, and I want only the 3 values, CD, CE, CF. CD is 6. CE is 1.3, and CF is 1.2. Almost there. D is I'm just going to look at DE and DF, and I have, excuse me, 1.2 and 3. And then finally I have EF, and EF has value 1. All right, and if I want to complete this chart, I sort of swap, I kind of reflect, like I'll send AC to CA, and this to here, and this to here, and this to here. So it's just kind of reflecting really over that diagonal line. 2, I get 2.2, I get 3, 3, 1, 7, 8, 5, 6, 1.3, 1.2, 1.2, 3, and 1. All right, so now I've filled out my table. And as I said, this table will sort of be given to you oftentimes instead of the graph. So the information might be like, okay, what's the distance between city D, Denver, and, oops. So what's the difference between, say, Denver and, Birmingham or something? And it's like, I don't know, well, it's more than 7 miles, but some unit of measurement will give you 7. Okay. All right. So you get this table and you want to perform this nearest neighbor algorithm. And so again, we're going to start at A, and what you do is you are going to look at A, look at the row of A and find the smallest value. And so we'll write down A, that's our first guy, and we're going to find the smallest value. And the smallest value here is 2. So, and now we look at that column, that's C. So A is out because well, A is out, but I guess we're going to want to connect up to A at the end, so I'm not going to erase it. But C is our next value, vertex. Maybe we should remember A, but I think we should actually eliminate A here. So since we're leaving A, we don't want to return to A until we're done, and then we'll return to A. So now we're on C, and we're going to look at the row of C here. which one is here? Which is the smallest value? And again, we don't want to return to A, so we will look and we'll find the smallest value is B. Well, we're out with C because we've already visited C. Okay, so we're going to write down C here as the next one. And now we're going to write down B as the third one. And now we need to go along the row of B. Okay. Looking at the row of B. And again, we don't want to return to A or C because we've already been there. So we find the smallest value, and F is the smallest value. So we'll go ahead and circle F, and I'll write down F as the next point. And now I can, again, I'm going to get rid of these guys. And now I move down to the row of F, and what do I have for F? Well, F is here. I don't want to return to any of the marked out vertices. So I have 3 and 1. 1 is the smallest value. So I go ahead and circle 1 and write down 1, write down E because E is what's next here. And again, you can now cross out F because we have F. And now you're on E. I mean, we're here. So if we look at E, you'll see there's not really any choice. You have only one, and you've already visited all the other vertices except D, so you have to go to D. So D is it. We'll write down D. And now we're done. I mean, we've gone A, C, B, D, A, C, B, F, E, D, and we return to A. And if you want, so when we know that we're going to DA, we can circle that in green as well, because we know we're going. And then if you add up all of the green, you will see that you get precisely this value here. So what I'm trying to say is there's this algorithm here that doesn't involve looking at a graph, but will produce the same effect. It will be the nearest neighbor algorithm, but without kind of drawing pictures. Okay, great. So I thought I would do one more example, which let me just draw it for you to illustrate another phenomena. So this we'll just make a green graph here, and I won't worry too much about making it too pretty here. But I'm going to put some weights or distances or costs on this. And I'm going to make one of these really far apart. Okay. All right, so let me label these vertices. A, B, C, D. Very simple graph, and it's meant to illustrate phenomena. So let's start at A, and let's see what we can come up with here. Okay. So if we start at A, what is the nearest neighbor? Well, the nearest neighbor is certainly B, right? Because 1.9 is the smallest of these three values. So we get B, and then the nearest neighbor to B is definitely C. It's only a distance of 1 away. And then we have an issue, which is that we're out of vertices. We've gone A, B, and C. The only thing left to do is D, and then we'll return to A. However, when we did this, we get a real extreme example of what we were just looking at. What is the total cost here? Total cost is 1.9 plus 1 plus 100 plus 3. So that's 105.9. So total cost is 105.9. And that looks pretty big. We kind of forced ourselves into this issue, but it looks pretty big. What if we started at B instead? So now let's start at B instead and see what happens. So if we start at B instead, we'll find that we get kind of the same thing. So if we look at B, although it's it may be a little different, but we get the same problem, I guess. If we look at B, we actually not quite. We don't get the same problem. So we're going to get a good situation here. So C is the closest neighbor, so it goes to C. But now, actually, now we have a situation where before, when we were at C, we couldn't return back to A because we had started at A. But now we can actually. So now we have two choices at C. So we can actually go ahead and go to A. And then, okay, now we don't have any choices. We must go to D, and then we can go back to B here. And so this is let's see, these are the two different paths. In one case, we got this path, this circuit. In the other case, we got this circuit. So they're different, and they're very different when it comes to cost. So the whole cost here is going to be what? Looks like 8. So we have a completely different cost, really hugely different cost, using the same algorithm. However, the only thing we did was we started at different vertices. So this process of saying, we want to calculate not just one nearest neighbor Hamiltonian circuit, but maybe all of them. And if you tried to start with C, we could pretty quickly see, okay, well, we get C, B, D, A, and C, and so this is sort of the opposite path to this. So these guys are both going to be 8, and then if we started with D, we would get D, B, C, A, D, and so this also is really the same as these guys. We get 8 here. So what I just did was I just performed what's called the repetitive nearest neighbor algorithm. And what happens here is that, okay, we know that we have an approximate algorithm. It's not going to always give us the optimal solution. Even this is not always going to give us the optimal solution, but we should at least check a lot of different possibilities since they're so easy to find before we kind of just go with the random one that we started with. And so this will give us, in principle, a better, a better solution than if we had just started with something random. All right, so that's the nearest neighbor algorithm. And next time we'll look at the cheapest link algorithm, and we will be finished with our Hamiltonian circuits. Okay,